All right, so in this section, we're going to pull everything together and we're going to be graphing these polynomials and rational functions using what we know about the first and second derivatives. So our strategies, we're going to start off with polynomials. Is the first thing we want to do is find the y-intercept. Okay, y-intercepts can be very helpful for us. It allows us to see where that graph is cutting the y-axis. And just find the x-intercepts when factoring as possible. If you can factor it, then generally your numbers are very nice and they're very easy to plot. If you can't factor, then don't go ahead and find the x-intercepts. The next thing we want to do is find the critical number. So we want to find where the function is increasing and decreasing, as well as any maxes or mins of our function f of x. So we need to find those critical numbers. Then we want to go ahead and find the concavity intervals and points of inflection. So this involves our second derivative. And we want to look at its end behavior. We want to find out the limit as the values of x approach infinity and negative infinity. And then we want to go ahead and sketch a little graph by hand. You can adjust the scale window of your graph. You can do a quick sketch by hand and you can get an idea of what the graph is doing. And you want to go ahead and compare it with your graphing calculator. If you're just in your graphing calculator, you're encouraged to sketch it first and then go ahead and put the function in the graphing calculator and go ahead and adjust your windows as you need to go ahead and do that. So let's go ahead and look at one example here. So here we have f of x is negative 2x cubed minus 9x squared plus 108x minus 10. Now notice here our leading value is negative, and we want to keep that in mind as we're going through these steps here. So we want to go ahead, we find our y-intercept, set x equal to 0, and we just end up with negative 10. Very easy, it's just a polynomial. And it is a cubic, and this one is not possible to factor, so we're not going to go ahead and find our x-intercepts in this particular case. Right? We're going to go ahead now and take our first derivative so we can find our critical values, our critical numbers. And we have negative 6x squared minus 18x plus 108. And we're going to go ahead and set that equal to 0. We set that equal to 0 and pull out the negative 6. Pulling out that negative 6 is going to change our signs. So our negative 18x, when we pull out the negative 6, it's going to change to a positive, as well as the 108 is now going to become negative. Pulling out that negative 6, we end up with x squared plus 3x minus 18. This is actually possible to factor, and it factors into x plus 6, x minus 3. So our critical values are either x is equal to negative 6 or x is equal to positive 3. So these are critical numbers. We're going to plot and test on the number line. And we're going to go ahead and test on negative 7 in our first derivative. We plug that in, it becomes negative. So this is a decreasing in that interval. It approaches negative 6, so we're going to pick a value between negative 6 and 3. 0 is the best bet. It's easy. It is positive in that case, and therefore it is increasing. In between negative 6 and 3, we're going to go ahead and pick 4 to the right of 3 for our last area, and we get a negative value, and so therefore the function is decreasing in here. Now this is not unexpected. This is a cubic function, so we kind of expected this to happen. So our intervals of decreasing, we're decreasing from negative infinity all the way up to negative 6. And then again at 3 to positive infinity. We're only increasing in between negative 6 and 3. And remember, we don't use brackets in that case. Right? We want to find our mins and maxes, so we go ahead and plug our critical numbers into our original function. So our minimum over here at negative 6 occurs at negative 550. And our maximum at 3 occurs at 179. So once you find those values, you could scale it as necessary on a hand graph, and then of course you would have to adjust your scaling on your graphing calculator when you check it. Now we're going to go ahead and find our concavity. So we need our second derivative. So our second derivative here is negative 12x minus 18. We're going to go ahead and set that equal to 0. And when we do, our x is negative 3 over 2. So now we're going to test for concavity at negative 3 over 2. We're going to test the value at negative 2. At negative 2 in our second derivative, we get a positive value. And to the right of negative 3 over 2, 0. 0 is a great number. And we end up with a negative value. All right, so we are concave up to the left, concave down to the right. So our concave up is negative infinity all the way to our value here at negative 3 over 2, our point of inflection. And it's concave down from negative 3 over 2 to positive infinity. And to find our actual inflection point, plug that value into our original function. And then we end up with negative 185.5 for our actual inflection point. Now we want to go ahead and look at our values as we approach infinity. Okay, remember our leading value here is negative 2x cubed. So if you know the shape of that here, the x cubed function goes up and does this, right? But remember here, it is a negative x. So our positive x cubed comes up from negative infinity and then goes up to positive infinity. And this one is flipped around, so it's going to do the exact opposite. It's going to come from high, it's going to come down. It's going to go ahead and hit our minimum. It's going to come back up for a little bit, and then it's going to go back down. It's going to match what we got from our first derivative. So here it's going to come down, come back up, and then go back down. It's because it's a cubic function. It'll maintain its shape. Okay. And then we want to look at the end behavior. Well, obviously it's going to be, if it's going up this way, because it comes down to a minimum, our limit as f of x approaches positive infinity is going to go up to infinity. Right? And then it's also going to go down to infinity on the other side based off the shape of the cubic graph. All right. So if we were to go ahead and draw this, all right, we're going to have, it's going to come from up here. It's going to come down to negative 6 because that's where the turning point occurs. It's going to go up between negative 6 and positive 3. And then it's going to go back down to infinity from there. And then we have our critical point here at negative 3 over 2. So this is where it's going to change right here. And then this is our y-intercept. Now notice this graph isn't perfect, and your hand graph does not have to be perfect. It should, in general, show the shape of the graph, and it should match pretty close. So here is our positive cubic graph. All right. And then this would be our version, or if it was positive, but because it's negative, it's going to flip from the other direction. Let's go ahead and look at another example. So we're going to go ahead and take x to the fourth minus 4x cubed. Now remember, x to the fourth functions are vaguely shaped like your x squared function. So we're expecting some sort of parabolic shape. And if we go ahead and figure out our intercept when x is equal to 0, y is equal to 0, so we have the origin. That's nice. And then we can go ahead and find our x-intercepts, because we can factor out an x cubed here. So when we go ahead and factor out an x cubed, we get x minus 4. So our x values, our x-intercepts are at 0 or 4. Okay, and of course our 0 is part of our y-intercept also, because that's our origin. We've already figured that out. And of course 4, 0 for our other x-intercept. So it crosses at the origin and at 4, 0. All right, we'll go ahead and find the first derivative. We have 4x cubed minus 12x squared. All right, again, we can go ahead and factor out an x squared as well as a 4 and set it equal to 0. So we have x is equal to 0 or x is equal to 3. Those are our critical numbers, so we want to see what the graph is doing at that point. And so at 0, we're going to test negative. To the left, we're going to test negative 1. When we go ahead and test -1 into our first derivative, it is a negative value, so it's decreasing. At to the right of 0, but before 3, we'll pick 1. And also it's decreasing at that value. So it's still decreasing past the origin, and it's going to continue that decrease. And then at +3, we want to look to a value to the right. We're going to pick 4. And it is increasing once it gets past +3. So our graph is decreasing from -infinity all the way to +3, because even on either side of 0, it's still decreasing. And then it's increasing from 3 to infinity. So again, that parabolic shape, it's decreasing, coming down to 3, and then it goes ahead and increases. So that's going to make this value here at 3 our min. Go ahead and plugging that min into our original function, we get -27. So our minimum is going to occur at 3, -27, which is what we expected. All right. Now, just because it decreased from 0 to 0, it could be an inflection point, but we won't know till I take our second derivative. So just because it was a value that we needed to look at, it could still be coming up later as an inflection point, as a turning point, but we're going to go ahead and look at that when we take the second derivative. So if we go ahead and take the second derivative, we get 12x squared minus 24x, set it equal to 0. Again, factoring out an x and a 12, we get x is equal to 0 or x is equal to 2. So here's that possible inflection point coming into play. So again, we have to test around 0 and 2. When we plug in any value here, let's say -1 to the left of 0, we end up with a positive value in our second derivative. In between 0 and 2, let's say 1, we'll get a negative value. And past 2 to the left there, we end up with a positive value again. All right, so this graph is doing a little bit of turning. Right, so it's going to be concave up right at this point here from -infinity to 0. It's also going to be concave up from 2 to +infinity. And it's going to be concave down in between 0 and 2. So from 0 to 2. So our 0, 0 was indeed an inflection point, as well as our 2, and we got to plug that in to our original function, and we'll get our -16. Right, let's go ahead and look at our end behavior. So our end behavior, this is a parabola, and it is, if you remember when we look, it's going down here, going to 3, and coming up. All right, if we looked at our first derivative. So when we go back to our end behavior, again, it's going to be doing that parabolic shape like this. All right, and the leading coefficient is greater than 0, so it's definitely an upright parabola. It's a positive parabola. So as the limit approaches -infinity, it's going to go to +infinity, and the limit to +infinity is also going to be +infinity. So our graph here is going to go ahead and look similar to this. It's going to come up from +infinity, go through the origin, go down to 3, or go down here to 2, come over here to 3, and then come back up. All right, and again, this isn't a perfect graph. Look at my scaling right here, but this is just a way to go ahead and do a rough graph, and you can get a more accurate representation in your graphing calculator. The next video is going to go ahead and cover our rational functions and graphing those.